Hello class! We're now in our second trial of this type of learning where I have the lectures and you'll do activities in class. And again, I'm not going to be there, so just listen, pay as close attention as you can, read the book, ask questions to your substitute, and hopefully they'll be able to help you. And if you ever come in something where you just don't understand, feel free to email me. So you're going to need your notes and maybe your textbook with you and a pencil so that you can fill in those notes. This chapter is about electric charges and current and how those work in our everyday lives. So first of all, a little bit of a review. We talked about how magnets, when like magnets attract each other or repel each other, and unlike magnet poles attract each other. We're going to talk about charges, electric charges. Remember, we have positive charges and negative charges in an atom. And when two protons, which are both positive, come close together, they repel each other. Or two electrons come close to each other, they're going to repel each other. And if we have a proton and electron that are coming close together, they're going to actually attract each other. Why does this happen? It's because they have different charges. And the names, actually positive and negative, that we give to charges were given to them by Benjamin Franklin in the 1700s. So, charges, the rules are the charges that are the same are going to repel each other, and charges that are different are going to attract each other. Again, it's the same rule as the interactions between magnetic poles. The difference, though, between magnets and the electric charges are that magnets never exist alone. When you have a north pole, you'll always have a south pole. If you have a south pole, you'll always have a north pole. But with charges, you can have a positive proton all by itself, or you can have a negative electron all by itself. So these two can stay separately, but magnets cannot. That is their difference. How are electric fields related to all of this? Remember, we had magnetic poles and they exert a force over a distance around the magnet. Electric charges do the same thing. They exert their force over a distance. This is called an electric field, the force that surrounds a charge and extends outward in every direction. If a charge is placed in an electric field, it's either pulled towards the electric field or pushed away based on the rules that we stated above. Like charges are going to repel, unlike charges are going to attract. And if you have your book on page 48, we're going to see how the single charges interact. In figure A, you have a picture of a positive charge and you have a picture of a negative charge. We can draw electric field lines around the charges. How do we decide which way those arrows are going to point? We're going to pretend that we're going to have a positive charge and put it in this electric field. So if my proton is positive and I put another positive charge in that top picture, they are like charges, so they're going to repel. So the magnetic field of a positive charge is outward. The arrows are pointing out. But the electric field around the electron, that negative charge, if we put a positive charge next to that negative charge, they're going to attract. So the electric field is actually pointing into that negative charge. The electric field is strongest right around the charge. You can see that the lines are closest together right next to that positive charge, and they're close together right next to the negative charge. And the field gets weaker and weaker as you get farther from that charge. If we have two charges close together, how do they interact? When there's more than one charge, those electric fields change and they actually combine. And again, just like magnets, if we have a positive charge and a negative charge, they're going to be pulled towards each other. They're going to be interacting in an attractive way. But if, like the bottom letter, figure B, we have two of the same charges. They are going to repel each other. So those fields are going to be moving away from each other, but they're still interacting. Now remember, we talked about all matter is made up of atoms. And all matter has these charged particles. They all have protons. They all have electrons. So why aren't all objects attracted or repelled to each other all the time? Why don't I get sucked into the wall because of positive and negative attraction? It's because, remember, every atom is neutral. We have the same number of protons as we have electrons. So every atom is neutral, even though they have these positive and negative charges. And therefore, they cancel each other out, and they don't attract or repel each other. However, we can charge objects. We can make something positive or negatively charged. If you remember, some electrons are able to move around their nucleus. They're always moving around, and some of them can actually leave their atom. But protons never leave. They're tightly stuck in the nucleus. So if we're going to charge an object, make it positive or negative, it's because the electrons are moving. Remember, electrons and insulators don't easily move, so they're not going to insulators don't get charged very easily. But conductors will be charged. Their electrons can leave or enter other atoms easily. Therefore, we can have a neutral object, no charge. It can become positive or negative if we gain or lose electrons. If the object loses electrons, it's actually going to become less negative and more positive because it has more protons than electrons. But if an object gains electrons, it's going to become more negative because it has more electrons than protons. What is static electricity? Static electricity is actually this buildup of charge on an object. We had a neutral object and we added more charge to it. That is called static electricity. It is different from electric current that goes through a wire because these charges aren't flowing. In static electricity, all those charges don't move. They're stuck on the object. But in current, those electrons are moving through a wire constantly. So how do we transfer? How do we get electrons from one object to another? There are a few different ways we can do this. First of all, we can have friction, the transfer of electrons from one object to another by rubbing. So in our picture on page 51, we can rub an object against another one, and we can transfer electrons directly by touch, by rubbing, and that is using friction. We can also use conduction, which transfers electrons from one charged object to another by direct contact. So I have an object that's already charged, and in your second picture, I put it on another object, and those electrons transfer to that second object because I touched it. Thirdly, I have induction. It's moving electrons from one part of an object to another because of an electric field. And that is in our the last picture. Charges within the spheres are rearranged, but not because of direct contact. They just are moved to different parts of the object because we put a negative close to it. The positive electrons were attracted to that negative rod, and they separated away from each other. That is induction. You don't actually touch anything, but the electrons still, those particles separate. In all of these examples, the charge was conserved. We did not lose, create, or destroy those charges. They just transferred from one object to another, and that's what we call the conservation of charge. Charge is not created or destroyed, they just transfer from one object to another. This is why we get static cling. Sometimes our clothes get stuck together, especially in the dryer. This is because those clothes are constantly rubbing against each other. Some clothes are negative, some clothes lose their electrons and become positive. And that, because of the positive and negative, they're attracted to each other and they're stuck until we pull them apart, and we hear that electric charge when we are pulling them apart. That is called static cling. It's because the positively charged objects are attracted to the negatively charged objects in your dryer. But sometimes we need to get rid of those electrons. How do we do that? How do we get these objects to go back to neutral? This is what we call static discharge. When a negatively charged object and a positively charged object come in contact with each other, the electrons are going to move between the two until they become neutral again, until the number of electrons is normal, is the same on both objects. This is what we call static discharge. The loss of static electricity, those electrons are stuck there, but they move, they are lost to the other object. They move to the other object. That is static discharge. We are discharging, we're getting rid of those extra electrons. Now on a humid day, when it's kind of wet feeling outside, the air is filled with a lot of water molecules. And those extra electrons don't transfer to other objects, they transfer to the water molecules. Therefore, we don't get as much static electricity when it's very wet outside, because all those electrons, they went to the water molecules in the air and not to other objects. How are sparks and lightning related to all of this? If you've ever walked across carpet, or maybe your shoes just picked up a lot of electrons and you touched a metal doorknob and you got shocked, like it's kind of sparked and you're like, ooh, that kind of hurt. That is the same concept. As you walked across the floor, you were picking up electrons. You're picking them up along the way. And when you went to touch that metal object, all the electrons went from you to the doorknob so that you both would become neutral again. So you had a big static discharge. All of your electrons were attracted to the neutral doorknob. And then when you touched the doorknob, the electrons jumped. Lightning is a very similar process. It's just a big spark. This is because as the air is moving, those water droplets in the clouds become more negatively charged. The electrons are attracted to all that movement, and to restore them back to neutral, because that's kind of the goal, is to be back to neutral, to normal, the electrons from the negative move to those positive areas. They spark and they discharge all that electricity to the positive areas. It can be a cloud, or it can even be the ground. Whichever one is closest, whichever one is easiest for that to discharge all of that electricity. Those electrons jump and it becomes an intense big spark, like the lightning that you see. Lastly, how can we detect if there is a charge in an object? There is something called an electroscope. The electroscope is a special device that can detect electric charges. It's made of, and there's a picture in your book on page 53, it's made of a metal rod and a knob that's placed inside of a glass bowl. Then, when the electroscope there are two pieces of metal at the bottom, called just two pieces of metal. When the electroscope is uncharged, those two metal pieces just kind of hang down, they're neutral. They're not charged at all. But if you put a charged object close to the electroscope, those charges, positive or negative, travel through the metal rod down to those pieces of metal, and they become charged. But remember, they're going to become the same charge. If we have a negative object, it's going to transfer all those negative electrons down to those two pieces of metal. And those two pieces of metal are now going to be both negative. What happens to objects that are both negative? They're going to repel, and so that those two pieces of metal are going to be pushed apart from each other, and you can tell this object has a charge because my two metal pieces spread apart because there are two like charges close to it. The same thing happens with positive charge. You take a positive object and you put it next to the electroscope. Those protons, they move down the rod, and then those two pieces of paper spread apart because protons and protons don't like each other. They're going to spread apart, and you know that object had a charge. The one thing you cannot do is tell, does this have a positive charge or a negative charge? This electroscope does not tell you that. It only tells you, yes, there's a charge, or no, there's not a charge. So in class, you're going to do a few activities with this, checking out some of the static charges, static cling, and just exploring a little bit with this static electricity. Ask questions, and hopefully this will make a little bit more sense to you tomorrow. Have a great day.